In the early dawn hours of late March 1945, a German submarine crew operated under the assumption that their latest technology had rendered them nearly undetectable. Commander Hartwig Lux had positioned his Type 7 U-boat at snorkel depth, approximately 40 nautical miles from the Isles of Scilly. The time was 4 in the morning, and conditions seemed ideal for their purposes. The diesel engines hummed steadily as they drew oxygen through the extended breathing tube, replenishing power cells that had been drained during more than half a day of underwater travel. Confidence pervaded the vessel. They maintained position 60 feet below the water's surface. No observation scope pierced the waves. The hull remained completely submerged. Only that slender tube connected them to the atmosphere above. Without warning, alarm conditions erupted throughout the submarine. The detection systems had provided no advance notice of approaching enemy vessels. Instead, explosive charges detonated with devastating proximity, hurling sailors against metal walls. 3 separate explosions surrounded the vessel in a coordinated pattern. Darkness engulfed the interior spaces. Backup illumination systems activated, bathing everything in crimson light. Seawater began spraying through compromised hull sections. Commands echoed through the compartments as the depth officer announced their uncontrolled descent. The commander struggled to comprehend the situation. They had been operating the snorkel system for 20 minutes using standard protocols. Ocean surface conditions included 3-foot waves providing additional concealment. Their radar warning equipment had remained silent throughout. Detection by aircraft should have been virtually impossible under these circumstances. Nevertheless, a British patrol plane had released its weapons with remarkable precision, targeting their exact position despite the snorkel creating almost no visible signature in these conditions. The submarine survived this engagement, eventually limping back to Bergen with structural damage and a traumatized crew. However, Lux and his sailors had experienced something increasingly common during the war's final phase. Allied aircraft were locating snorkeling submarines with disturbing regularity, detecting them through methods German forces did not fully comprehend. The snorkel technology, intended as the answer to Allied radar capabilities and air dominance, had transformed into something quite different. It had become a vulnerability that made submarines predictable and ultimately discoverable through detection. Equipment most submarine commanders had never encountered. The device that located this U-boat was designated a magnetic anomaly detector. Rather than relying on visual observation, radio wave reflection, or acoustic signals, it identified the massive steel structure of submarines by measuring minute disturbances in the planet's magnetic field. It was finding snorkeling submarines because those vessels, believing themselves concealed, were traveling in straight lines at consistent depths, making themselves ideal targets for a detection system requiring precise flight patterns to function effectively. The assurance German submariners placed in their snorkels, the conviction that this equipment had restored their capacity to operate safely in Allied-controlled waters, was about to be systematically undermined by physics they could not evade and defensive measures they did not know existed until too late. The snorkel had not originated as a German innovation. Dutch naval engineers had created the apparatus in the late 1930s, installing it on their submarines as a method to operate diesel engines while submerged at periscope depth. The principle was straightforward. A retractable tube extended above the surface, drawing air down to the engines, while a second tube expelled exhaust. The submarine could recharge its batteries and refresh its air supply without fully surfacing, reducing vulnerability to air attack and surface radar detection. When Germany invaded the Netherlands in spring 1940, the naval forces captured Dutch submarines and examined their snorkel systems with interest. Initially, however, German naval leadership did not perceive the value. In 1940 and 1941, U-boats operated with relative freedom. The period submariners called the happy time allowed U-boats to surface freely, run on diesel engines at high speed, and attack Allied convoys without significant air threat. Wolf pack tactics were proving effective. Tonnage destroyed was mounting. The Battle of the Atlantic appeared to be progressing favorably. The snorkel remained merely a curiosity, a Dutch innovation addressing a problem Germany did not yet face. That situation changed in 1943. Allied air power over the Atlantic increased dramatically. Long-range patrol aircraft began covering areas previously beyond aircraft range, closing the gap where U-boats had operated safely. Escort carriers brought aircraft to convoy routes. Coastal Command flew constant patrols, and critically, Allied radar technology improved, to the point where surfaced U-boats could be detected at night and in poor weather, conditions that had previously provided concealment. Centimetric radar operating at wavelengths around 10 centimeters proved devastatingly effective. U-boats equipped with radar detectors that monitored for earlier meter-wave systems found themselves surprised by the new technology. Aircraft appeared without warning. U-boats were being caught on the surface, unable to dive quickly enough to escape attack. Losses mounted significantly. In May 1943 alone, Germany lost 41 U-boats. The crews called it Black May. For the first time in the conflict, U-boat losses exceeded replacement capacity. Grand Admiral Karl Dönitz, commander of the U-boat force, faced a crisis. His submarines could no longer operate safely on the surface, but submerged operation was severely limited. Batteries provided power for only a few hours of underwater movement before requiring recharge. To recharge batteries, U-boats had to surface and run diesel engines, exposing themselves to the very air patrols that were destroying them. The Dutch snorkel suddenly became relevant. If U-boats could run their diesels while remaining submerged, they could avoid radar detection while maintaining battery charge and operational range. Development and installation began in earnest in late 1943. The German version was engineered for retrofitting to existing submarines as well as inclusion in new construction. The device consisted of two tubes, housed in a single streamlined assembly that could be raised and lowered hydraulically. The head valve, a critical component, featured a float mechanism that automatically closed when waves washed over the snorkel, preventing water from flooding into the boat. By spring of 1944, U-boats began returning to Atlantic patrols equipped with snorkels. The initial results seemed promising. U-boats could remain submerged for weeks, surfacing only rarely for navigation fixes or emergency repairs. They avoided radar detection. Aircraft sightings decreased. Submariners felt they had regained the initiative, that German engineering had once again provided a solution to Allied technological advantages. Commanders reported successful patrols. Crews developed procedures and techniques. They learned to snorkel in rough weather when the waves provided additional concealment for the mast. They learned to maintain precise depth control, keeping the boat stable at snorkel depth despite sea conditions. Inside a snorkeling U-boat, conditions were miserable. When the head valve closed due to wave action, which happened constantly in anything but calm seas, the diesel engines continued running, drawing air from inside the pressure hull. The resulting pressure differential was immediate and painful. Eardrums popped. Sinuses ached. Men felt crushing pressure in their chests. When the valve reopened and air rushed back in, the pressure equalized violently, sometimes causing nosebleeds and severe headaches. The diesel exhaust system, despite engineering efforts, leaked. Carbon monoxide seeped into the crew compartments. Men developed headaches, nausea, and confusion. Some lost consciousness. Every snorkeling patrol meant enduring these conditions for hours at a time, sometimes for days on end when tactical situations prevented surfacing. However, submariners accepted this. They believed the alternative of surfacing into Allied air patrols was worse. The snorkel, despite its discomforts, seemed to offer survival. German communications reinforced this belief. Reports emphasized U-boats successfully evading Allied patrols. Technical journals discussed the snorkel as a superior solution to Allied radar. Training emphasized snorkeling as the primary operating mode for all future patrols. The magnetic anomaly detector was not a radar system. It did not transmit signals and wait for reflections. It was a passive sensor measuring something submarines could not hide: the distortion their steel hulls caused in the planet's magnetic field. The principle was straightforward. Earth generates a magnetic field, invisible but measurable, that varies slightly depending on location and local geological conditions. A large ferrous object like a submarine hull containing hundreds of tons of steel creates a localized distortion in this field, an anomaly that sensitive instruments can detect. Development of practical detection equipment began in the United States in 1941 at research laboratories in Pittsburgh. Physicists and engineers worked to create a detector sensitive enough to identify submarine-sized magnetic anomalies, while being robust enough for military use aboard aircraft bouncing through turbulent air. The challenge was substantial. The magnetic signature of a submerged submarine was minute compared to the planet's background magnetic field. Detecting it required instruments capable of measuring variations as small as 1 part in 50,000 of the total field strength. By 1942, working prototypes existed, The detector consisted of a magnetometer housed in a streamlined tail assembly extending behind the aircraft. This placement, far from the aircraft's own steel structure and engines, minimized interference. The magnetometer used a saturable core induction coil design. Changes in the magnetic field induced electrical currents in the coil, which were amplified and displayed to the operator. The effective detection range was limited by physics. The system could detect a submerged submarine at approximately 400 yards laterally and up to 150 feet in depth. These were not long ranges. Unlike radar, which could detect surfaced vessels at several miles, this system required the aircraft to pass almost directly over the submarine. This necessitated precise search patterns and careful navigation. Aircraft equipped with magnetic detectors flew systematic parallel tracks covering areas where submarines were suspected or reported. The US Navy began operational deployment in 1943, initially aboard flying boats and later on patrol bombers, operating from escort carriers. The British received equipment through Lend-Lease, installing it primarily on maritime patrol aircraft. By 1944, hundreds of Allied patrol aircraft carried magnetic detectors, particularly those assigned to anti-submarine warfare in critical areas: the Bay of Biscay, the English Channel approaches, the waters around Gibraltar, and the convoy routes south of Iceland. Operators required training to interpret the equipment. The detector produced a continuous trace on a paper chart recorder, drawing a baseline showing normal magnetic field strength. When the aircraft passed near a submarine, the trace spiked sharply upward or downward, depending on the submarine's magnetic orientation. The operator watched this trace constantly during patrol flights, calling out contacts to the pilot and bombardier. False contacts were common. Shipwrecks on the ocean floor, geological formations, even schools of certain fish could produce small anomalies. However, the signature of a submarine was distinctive: a sharp, symmetrical spike that rose and fell quickly as the aircraft passed overhead. The real power of magnetic detection was not in long-range detection. It was in providing precise localization for weapons delivery. Once radar or visual observation identified a general area where a submarine might be operating, magnetic detection allowed aircraft to pinpoint the exact location for depth charge or acoustic torpedo drops. Critically, this system worked against snorkeling submarines that had no hull breaking the surface, no large radar signature, and minimal visual profile. The snorkel mast itself was nearly undetectable by radar and almost impossible to spot visually, except in calm seas. But the submarine's steel hull 60 feet beneath that snorkel created the same magnetic anomaly, whether snorkeling or fully submerged. The pattern emerged slowly through operational analysis conducted at submarine tracking facilities in Liverpool and at US Navy headquarters in Washington. U-boats equipped with snorkels were being attacked at higher rates than expected. More significantly, they were being attacked while snorkeling in conditions where visual or radar detection should have been nearly impossible. At night, in rough weather with only the snorkel mast exposed. Analysis in February 1945 revealed the correlation. Aircraft equipped with magnetic detectors were achieving attacks on snorkeling U-boats at rates substantially higher than visual or radar contacts would predict. In one 10-day period, 7 separate attacks occurred on submerged contacts in the western approaches. 4 of those attacks resulted in confirmed U-boat kills. 3 more damaged submarines that limped back to French or Norwegian ports. The tactical situation that made magnetic detection so effective against snorkeling U-boats was predictability. A U-boat running on the surface could maneuver freely, changing course and speed unpredictably. A fully submerged U-boat running on batteries moved slowly and often crept along near the bottom, making it difficult for aircraft to maintain contact. However, a snorkeling U-boat operated under specific constraints that made it an ideal target. To snorkel effectively, a U-boat maintained a precise depth, typically between 50 and 70 feet, keeping the snorkel head just above the surface. The submarine needed to run straight and level, because any significant maneuvering risked the snorkel breaking the surface too far, making it visible, or dipping too deep, allowing waves to flood the head valve continuously. Speed had to be moderate, usually 6 to 8 knots, fast enough to make progress, but slow enough to maintain depth control and prevent excessive snorkel wake. These operational requirements meant snorkeling U-boats moved in predictable patterns. Once detected by any means, aircraft could search likely areas with magnetic detection, flying systematic patterns at low altitude. When the magnetic trace spiked, the bombardier released weapons immediately. The U-boat, constrained by snorkeling depth and limited ability to maneuver quickly, often remained within the weapon's lethal radius. Multiple U-boats experienced this fate in spring 1945. One boat was detected while snorkeling northwest of the Hebrides after 3 hours of operation. Weather was overcast with moderate seas, conditions the crew believed provided concealment. A British patrol aircraft equipped with magnetic detection and operating in the area based on intelligence estimates picked up the magnetic signature. The aircraft made passes to confirm the contact. Depth charges destroyed the boat. 49 men died. The pattern repeated across operational areas. U-boats snorkeling in the Irish Sea, the western approaches, the waters around the Faroe Islands and the Norwegian Sea were being found and destroyed. The operational calculus that had once favored submarines, with the vast ocean providing concealment and the difficulty of finding a small vessel in enormous search areas, had shifted decisively against them. Magnetic detection did not need to search vast areas effectively. It only needed to search areas where submarines were likely to be, where intelligence suggested they might operate, where probability and operational necessity forced them to transit. German submariners adapted as best they could with the information available to them. Some commanders began snorkeling only during daytime hours, reasoning that aircraft operations were slightly reduced at night, though this adaptation provided minimal benefit since magnetic detection worked regardless of light conditions. Others snorkeled only in the worst weather, believing storms would keep aircraft grounded, which was partially effective but also made snorkeling itself more dangerous. Some crews requested assignment to newer submarines with massive battery capacity that could operate submerged for extended periods without snorkeling. These boats, designed specifically to counter Allied air superiority, featured streamlined hulls for high underwater speed and enough battery power to run submerged for 2 to 3 days at patrol speeds. However, only 2 of these advanced boats completed operational patrols before the war ended. German shipyards, devastated by Allied bombing and starved of raw materials by collapsing supply lines, could not produce them in meaningful numbers. German naval intelligence knew Allied aircraft possessed some kind of improved detection capability by late 1944, but they struggled to understand how it worked. Interrogations of captured Allied aircrew occasionally mentioned magnetic detection equipment, but these reports were fragmentary and often dismissed as disinformation. The concept seemed implausible to German engineers who understood the theoretical difficulties of detecting magnetic anomalies from aircraft. Senior staff officers compiled reports of suspicious attacks throughout the winter of 1944 and 1945, noting that U-boats were being attacked while snorkeling under conditions where conventional detection methods should have been ineffective. They theorized that Allies might have developed extremely sensitive radar capable of detecting the small snorkel mast or possibly infrared detection systems that could identify the warm exhaust gases from diesel engines. The truth was simpler and more inescapable than German planners realized. Magnetic detection identified the one thing submarines could not hide: their steel hulls. No amount of tactical adaptation could eliminate a submarine's magnetic signature. Unlike radar signatures that could be reduced through design and materials, or acoustic signatures that could be quieted through engineering, the magnetic anomaly was fundamental to the submarine's construction. Hundreds of tons of steel in a long cylindrical shape created a predictable, detectable distortion in the planet's magnetic field. For U-boat crews, learning about magnetic detection through rumors and fragmented reports that filtered through the submarine service, the realization was deeply unsettling. The snorkel, which they had believed made them nearly undetectable, had instead made them more vulnerable by forcing them into predictable operating patterns. They ran straight and level at consistent depths, perfect targets for a detection system that required aircraft to fly precise search patterns. One warrant machinist recorded his thoughts in a journal later recovered from wreckage. When his boat was sunk in May 1945, his entry from late April described the crew's growing awareness that something was wrong. He wrote about how they snorkeled believing themselves safe, how the commander said the snorkel made them invisible to enemy radar, but boats were not returning. The English were finding them somehow. They did not understand how, but they were being found. The psychological impact extended beyond individual crews to the institutional level. The snorkel program had consumed enormous resources: engineering development, manufacturing capacity, installation time in shipyards, and crew training. It represented the Navy's primary technical solution to Allied air superiority. If the snorkel did not provide the protection it promised, if Allied aircraft could find snorkeling U-boats as easily as surfaced ones, then the entire operational concept of late-war U-boat warfare was flawed. Dönitz, in his capacity as Commander-in-Chief of the German Navy, faced an impossible situation. He could not withdraw the U-boats from operational areas because Hitler demanded they continue attacking Allied shipping to disrupt the supply lines supporting the invasion of Europe. He could not order boats to surface and run on diesel engines because Allied air patrols would destroy them even faster than they were being destroyed while snorkeling. The snorkel remained the least bad option, even as evidence mounted that it provided less protection than originally believed. This paradox defined the final months of the U-boat war. From January through May 1945, German submarines continued operations under increasingly desperate circumstances. Boats departed Norwegian bases knowing their chances of survival were minimal. Crews understood the mathematics. More U-boats were being sunk than were sinking Allied ships. In April 1945 alone, 55 U-boats were lost. Many were destroyed while snorkeling, caught by magnetic detection-equipped aircraft that found them in waters where visual or radar detection should have been nearly impossible. The Bay of Biscay, once a transit route for U-boats moving between French bases and Atlantic patrol areas, became a killing ground. Allied aircraft flying systematic, search patterns with magnetic detectors found snorkeling U-boats with regularity that German commanders could not explain. Multiple submarines departed Norwegian bases in April 1945 under orders to operate against Allied shipping lanes. Many never reached their patrol areas. Aircraft detected them while snorkeling and dropped depth charges. The boats went down with all hands. This pattern repeated across operational areas. U-boats snorkeling in the Irish Sea, the western approaches, and the Norwegian Sea were being found and destroyed. The operational calculus had shifted decisively. Magnetic detection did not need to search vast areas effectively. It only needed to search areas where submarines were likely to be, where intelligence suggested they might operate, where probability forced them to transit. German submariners adapted as best they could. Some began snorkeling only during daytime hours. Others operated only in the worst weather. Some requested assignment to newer submarines with massive battery capacity, but these advanced boats could not be produced in meaningful numbers before the war ended. The U-boat crews who survived until Germany's surrender in May 1945 emerged from a campaign that had consumed the submarine force almost entirely. Of the roughly 1,150 U-boats commissioned during the war, 785 were lost. 30,000 men served in U-boats. 28,000 died, a loss rate of 75%, the highest of any military service in any nation during World War II. The surrender of the U-boat fleet in May 1945 provided Allied intelligence with unprecedented access to German submarines, equipment and documentation. Technical intelligence teams examined captured boats, interviewed survivors, and analyzed operational records. What they discovered confirmed what operational data had already suggested. German submariners had been operating with incomplete understanding of Allied detection capabilities throughout the final 18 months of the war. Analysis of German U-boat logs recovered from surrendered vessels and captured bases revealed that U-boat commanders attributed their losses primarily to improved Allied radar and increased air patrols. Few mentioned magnetic detection. Most had never heard of the technology. The system that had contributed substantially to U-boat losses in the war's final year remained largely unknown to the men it was killing. This intelligence asymmetry had proven decisive. German engineers had developed the snorkel as a countermeasure to radar detection, and the snorkel worked as designed. It reduced radar signature dramatically. However, Allied forces had already moved beyond radar as their primary anti-submarine detection method in scenarios where U-boats use snorkels. Magnetic detection provided the capability to find submarines that were otherwise nearly invisible, exploiting the very operational patterns that snorkeling required. British and American technical experts who examined captured submarines with snorkels installed noted the engineering quality of the equipment. The snorkel masts were well designed with effective head valves and reliable hydraulic raising mechanisms. The integration into existing boats was competent. The equipment worked as intended, but it solved the wrong problem. Or rather, it solved the right problem while inadvertently creating vulnerability to a different threat that German planners had not Anticipated post-war analysis calculated that magnetic detection-equipped aircraft achieved successful attacks on snorkeling U-boats at roughly 3 times the rate of aircraft without this technology operating in similar areas during the same period. The technology was not a silver bullet. Most kills still came from convoy escorts using sonar or from aircraft using radar to catch U-boats on the surface. However, in the specific tactical scenario of hunting snorkeling U-boats, magnetic detection provided a significant advantage that German forces had no effective counter for. The human cost of this technological asymmetry was measured in U-boat crew rosters and loss reports. Each entry in the loss ledger represented 50 men, most in their early 20s, who died believing their snorkels provided protection that, against magnetic detection-equipped aircraft, they did not provide. They snorkeled according to doctrine, maintained proper depth, followed procedures, and died when depth charges found them anyway. Survivors struggled with the revelation. Some commanders who survived the war wrote about learning that Allied aircraft had been detecting U-boats through magnetic signatures. Their reactions mixed disbelief with anger. Disbelief that such technology existed and could work effectively. Anger that German intelligence had failed to identify this threat and develop countermeasures. They described conversations with other surviving commanders who expressed similar feelings. A sense that they had been fighting blind, unaware of the capabilities arrayed against them. The snorkel itself continued service in post-war navies. The concept was sound. Submarines could benefit from running diesel engines while submerged. Every modern diesel-electric submarine built after 1945 incorporated snorkel technology in some form. However, the tactical situation changed. Post-war submarine doctrine emphasized deeper operations, faster submerged speeds, and better understanding of detection threats. The predictable straight line, snorkeling at fixed depth that characterized German operations in 1944 and 1945 became recognized as tactically dangerous. Magnetic detection technology also continued development. The US Navy improved detector sensitivity and installed equipment on helicopter, anti-submarine platforms where the ability to hover over a suspected contact made the systems short, detection range less limiting. Soviet submarines faced magnetic detection-equipped aircraft throughout the Cold War. Modern maritime patrol aircraft still carry magnetic detectors, though their importance has diminished relative to other sensor systems. The story illustrates a fundamental truth about technological warfare. Solutions create new problems. Advantages exist only relative to adversary capabilities, and the gap between what forces believe about their equipment and what that equipment can actually accomplish often determines survival. German submariners believed the snorkel made them invisible. They were wrong. Allied forces had developed a detection method that did not care about radar signatures or visual profiles. It detected the inescapable physics of hundreds of tons of steel displacing the planet's magnetic field. This was not a failure of German engineering. The snorkel worked. It accomplished its design purpose of allowing submerged diesel operation. The failure was strategic and institutional. The failure to understand that adversaries would adapt, that technological advantages were temporary, that the enemy was developing capabilities in laboratories and testing ranges that would only become apparent when they began destroying U-boats at sea. By the time German submariners realized Allied aircraft were finding them through methods their equipment could not detect or counter, it was too late to develop responses. The war was ending. The U-boat force was being destroyed faster than it could be replaced. Commander Lux, whose submarine survived the attack described at the beginning, surrendered his boat in Bergen the day after Germany's capitulation. His crew, shaken by their experiences, learned during surrender processing that Allied aircraft had been using magnetic detection equipment. Lux later told British interrogators that knowing this information earlier would not have changed tactics significantly. U-boats still needed to snorkel to charge batteries, and there was no practical way to shield a submarine's magnetic signature while maintaining operational capability. However, the knowledge would have changed expectations. Crews would have understood that snorkeling offered concealment, not invisibility, that risk remained despite following procedures, that survival depended as much on luck as on proper operation. The broader lesson extends beyond U-boats and magnetic detection to the nature of technological competition in warfare. The side that understands both its own capabilities and its adversary's capabilities holds an enormous advantage. The side operating with incomplete information, believing its countermeasures are effective when they are being systematically defeated by unknown methods, faces not just material disadvantage but psychological disadvantage. Confidence built on false assumptions collapses when confronted with reality, leaving forces demoralized and tactically confused. For the 28,000 men who died in U-boats during World War II, many in the final months while snorkeling under the belief that they were protected, the lesson came too late or not at all. They climbed into their boats, submerged to snorkeling depth, ran their diesels, recharged their batteries, and continued their patrols. Some completed their missions and returned to base. Most did not. They remain in their steel coffins on the ocean floor, casualties of a technological race they did not know they were losing until the depth charges came down and the pressure hulls collapsed and the Atlantic took them. The morning in late March 1945, one U-boat crew believed their snorkel made them invisible. By the time the depth charges exploded around them, they knew differently. They were among the fortunate ones. They survived to learn the truth. Thousands of their comrades did not. They died believing the snorkel protected them, never knowing that Allied aircraft above them were following traces on paper charts, watching magnetic anomaly detectors spike as they passed over submarines that thought they were hidden, but were in fact as visible as if they had been running on the surface in broad daylight. The Type 7 U-boat, the most common submarine in the German fleet, measured approximately 67 meters in length with a beam of just over 6 meters. The pressure hull, constructed from heavy steel plates riveted and welded together, could withstand depths up to 200 meters under normal conditions, though emergency dives occasionally pushed boats deeper with catastrophic results. The crew complement numbered between 44 and 52 men, depending on the specific variant and mission requirements. These submarines operated on a dual propulsion system that defined their operational characteristics. On the surface, two supercharged diesel engines, each producing between 1,400 and 1,600 horsepower, drove the vessel at speeds approaching 17 knots. These engines were marvels of German engineering, compact and powerful, but they consumed oxygen voraciously and produced exhaust that required venting to the atmosphere. Submerged, the boat switched to electric motors powered by massive lead-acid battery banks. These batteries, weighing many tons and occupying substantial space in the lower hull sections, could drive the submarine at speeds up to 7 or 8 knots for short periods, but sustained underwater travel required reducing speed to 4 knots or less to conserve power. The snorkel installation added approximately 2 meters to the submarine's overall height when extended. The device consisted of a main air induction tube, roughly 30 centimeters in diameter, and a smaller exhaust tube. The entire assembly could be raised or lowered through a watertight housing using hydraulic pressure. The head valve mechanism at the top incorporated a float design that would rise and seal the intake when waves washed over it, a simple but critical safety feature that prevented flooding. The engineering challenges of retrofitting snorkels to existing submarines were considerable. Shipyard workers had to cut through the pressure hull to install the snorkel housing, then ensure perfect watertight integrity around the installation. The hydraulic systems required careful integration with existing boat systems. The diesel engine exhaust routing had to be modified to vent through the snorkel rather than through the original deck exhausts. Each installation required several weeks of shipyard time, during which the submarine was unavailable for combat operations. The physical conditions inside a snorkeling submarine tested human endurance in ways that surface naval operations never approached. The interior of a Type 7 submarine, even under the best conditions, was cramped beyond modern comprehension. Men lived in spaces barely large enough to accommodate their bodies. Bunks were stacked 3 high with perhaps 18 inches of clearance between each level. Sailors slept in shifts, sharing bunks with crew members on opposite watches, a practice called hot bunking because the bedding never cooled. When snorkeling, these already difficult conditions became nearly unbearable. The head valve closure created pressure differentials that could reach 1/10 of an atmosphere or more within seconds. Sailors described the sensation as being suddenly transported to a mountaintop altitude. Ears popped painfully. Sinuses that were congested or infected caused excruciating pain. Men with dental problems found that teeth with cavities or imperfect fillings would throb or crack under the pressure changes. The diesel engines, running inside a sealed hull, consumed oxygen from the crew spaces when the head valve was closed. Sailors would gasp for breath, feeling their lungs working harder against the thinning air. Some men fainted. Others vomited from the combination of low oxygen, high carbon dioxide, and the constant motion of the boat. When the head valve reopened, air would rush back into the submarine with a roar, equalizing the pressure so violently that it could knock lightweight items off shelves and throw loose papers around the compartments. Carbon monoxide poisoning was an ever-present danger. The diesel exhaust system, no matter how carefully maintained, developed leaks. The exhaust gases contain not just carbon dioxide but carbon monoxide, a colorless, odorless poison that bound to hemoglobin in the blood more readily than oxygen. Early symptoms included headaches, dizziness, and nausea, easily confused with seasickness or the effects of pressure changes. As exposure continued, men became confused, their judgment impaired, their reactions slowed. Some crew members would lose consciousness without warning. Sailors learned to watch each other for signs of carbon monoxide poisoning, knowing that a man affected by the gas often could not recognize his own symptoms. The humidity inside the submarine approached 100%. Condensation formed on every metal surface. Water dripped constantly from overhead pipes and electrical conduits. Bedding became damp and never dried. Clothing stayed wet. Mold grew on leather items, on paper, on food. The smell inside the submarine was infamous among submariners. A combination of diesel fuel, unwashed bodies, mildew, cooking odors, and the acrid smell of battery gases that occasionally leaked from the battery compartments. Food quality deteriorated rapidly. Fresh provisions lasted only a few days before spoiling in the humid environment. After the first week, the crew subsisted on canned goods, preserved meats, and dried foods. Bread became moldy within days. Fresh water was severely rationed, used primarily for drinking, with little available for washing. Men went weeks without bathing. Toilets could only be flushed under specific conditions related to depth and sea pressure, requiring complex valve operations that, if done incorrectly, could result in sewage being blown back into the submarine under pressure.